First Spin. Welcome to First Spin, a show where I learn how to use the parallax propeller without having any prior programming experience. Rather than do this on my own, I have enlisted the help of two experts.
We really get to be experts this week.
It's true.
Yeah.
Right, because we got to talk about a bunch of strange stuff.
Yes. And it all looks like symbols to me.
Now, first off, we waited a little bit late into the show last week to sort of explain a little something to Addie here, so we're going to kick off with that.
Operators.
Right.
I should, by the way, mention that we are in probably full, either just past or full swing of
Traveling.
Yeah, we're in California right now. This is pre-recorded, so we're off having a good time while...
Meta.
Well, on Tuesday I guess you are still in California. You're at my house.
Okay, so time traveling us is 2 weeks in the future at Roy's house.
I think, is that right?
Yeah.
I need to check my
'cause
calendar.
Tuesday is when we drive down to my house from Joe's house.
No. This one.
Oh, is it Wednesday?
No. We actually haven't left for California,
Oh.
I think. Right?
We're confusing
No.
ourselves
Let's
with-
see. This would be the day that we actually leave for California.
Yes.
This episode.
We are
this
leaving.
Is when we leave.
We are en route. We're going to
Yes.
go pick up Peter.
Yes.
It's next week that you'll be at my house.
Right.
That's right. Future next week, not
Future next week. We get it. We're just terribly excited.
It's all very
When this show
complicated.
is airing, I will be in Rockland.
Right.
Roy will be in
Or
California. We're hitting the road and we're
The 10th?
driving
You're going to be in Rockland already.
I'm
all the
leaving-
way across the United States to go to the Parallax
Expo.
Expo.
People are going to be so sick of us hearing about us talk about this expo.
Well, you know,
We're just excited. We're excited.
I'm sure everybody else who's going is excited too.
I know.
It's going to be a big one.
It's going to be a big one. I don't know where we're going to park, but
I want to see that quadcopter competition stuff that they're going to have. It's
yes,
going
and
to be crazy.
they have a robotics competition.
I've never seen a quadcopter in person, so
Really?
it's going to be great.
Me neither. Can I fly yours?
Yeah, well,
I would not agree to that, Roy. That's an
you might
expensive
kill somebody
toy.
if I let you fly mine. Ken will let you fly his. He let me
Uh-oh.
fly his, and I crashed it.
Nice. Well, I
Pretty
just wanted to float
Yeah.
a little bit, hover, you know.
Ken probably just looks at it as an excuse to add upgrades. It's like, hey, you could fly this. Smash.
Yeah.
Oh dear, it broke. Maybe I should add bigger motors.
Maybe.
Okay, so
Wait.
back to
Okay.
binary
Yeah. Binary operators. Let's.
okay, so just to cover what I mentioned at the very end of the last show. So binary operator is an operator that has two inputs.
Mm-hmm.
Typically think of them as the left and right input, and it's because it's the one that's on the left side of the operator and the other one's on the right side of the operator.
Like X would be one and Y would be one, and
Yeah,
plus would
so
be the operator.
in the case of, X : Y,
Yep.
X is the left and Y is the right.
Right. : equals is the
Assigning-
operator.
Yeah, and you're assigning Y, the value that's in Y, into X.
That makes
And
sense.
So in the manual on page 43, for those following along, there's two columns,
Yep.
right?
Yep.
And one column is just the operator doing its thing on the two inputs.
Yep.
And the right column is the operator with assignment also.
Yep.
And what that means is that it's taking the left and the right and doing the operation, whatever it is, plus, minus, times, whatever,
Yep.
and then assigning it into the left one.
Yep.
So if you had X plus equals Y, it would do X plus Y and then assign
Mine
it
into
into X.
X. Okay. Yep.
So this is going to apply to pretty much all of these, Addie. So we're going to be able to tear through them if you understand that that's going to be true about every single one of these.
So X
Right.
minus Y, or X minus equals Y would be X minus Y placed into X.
Yes.
Right.
If it's just minus, then it's just X minus Y placed
Yep.
into
Right.
whatever it is, whether that could
Right.
be A or whatever.
Yeah, we covered the
Well-
add version of this last week.
Okay.
Right.
And then multiply is the same thing. Do I need to be concerned about this return lower 32 bits bit?
Yes.
Right. So with multiply and spin, when you do the multiply, you have two 32-bit values that you're multiplying by each other.
Yeah.
And the result is actually
the lower 32.
Well, no. The total result, ignoring that for a second, of multiplying two 32-bit numbers is actually a 64-bit number.
Uh-huh.
But you can't, the spin only deals with 32-bit values, so a normal multiply is only going to give you the bottom 32 bits of that full result.
Right. Okay.
So that's the star or star equals.
Now, how
and you can abuse that to do interesting things too.
I have a question. So the top bit usually represents the sign.
Right.
Which, if multiplied, would be the 63rd bit, would be bit 63, right?
Mm-hmm.
Whatever. So how does that sign get transferred to the lower 32 bits?
That's what I'm just trying to...
Oh.
that is an interesting question right there.
Right?
Yep.
Right.
I hadn't really ever thought about that, and I'm trying to see.
I'm gonna assume that it inherits the sign, and that it's not the lower 32 bits, it's the lower 31 bits, and it inherits the sign from the overall sign. Because otherwise, it would just cause all sorts of strange math to occur, and it doesn't cause strange math. So
it doesn't actually say.
Oh.
Maybe we need to report this to Parallax.
Maybe we need
to report this.
Manual
doesn't quite cover an important case.
I'm going to guess that it's what I said, because that's what makes sense.
Yeah.
But
yeah, you're probably right. I mean, it has to.
Because if it were flipping that sign bit randomly as it splits this number into two halves, then it would be the wrong number.
Well, when you think about it, if the values are small enough, then the sign bit is going to go all the way down into the top of the 32-bit value. So it would work out as long as the value wasn't too big. And if the value was larger than, if it wrapped, it actually becomes positive, so it doesn't matter, and it actually doesn't need to replicate the bit.
So does it just work out with your two's complement crazy negative stuff we talked about a couple weeks ago?
Yeah, I'm pretty sure that it actually does work out.
Huh.
So the value, because you have to think about it in the context of, if you only care about the 32 bits and you just ignored the upper 32 bits, it wraps around when you multiply a number that's too big by another number that's too big, so that the result doesn't fit into 32 bits. The bottom 32 bits is still the correct result of it wrapping around.
Now,
staying a 32-bit value.
Some of our long-term listeners here will remember a few months ago when I went off on a little rant about how much I dislike signed numbers, and how I just like unsigned numbers, because when you're dealing with unsigned numbers, you don't have to deal with all this crazy
nonsense
stuff.
Yeah.
Now, being able to have negative is very useful too. Don't get me wrong.
Right.
But, so much easier to deal with.
So it doesn't mention it because it doesn't need to, really. So I don't think we need. They might want to put a note, but that's a minor thing. So it works out that it just wraps, and you could just ignore the fact that there's an upper 64 bits.
So it wraps the lower to the lower 32, whereas the next one wraps to the upper 32 bits.
No. What the next one is doing the math. It just gives you what the upper 32 bits would be.
And by the next one, they're talking about we were just talking about star equals. The next one is star equals.
Right.
So this is where you can multiply the star on the non-assignment side.
Right.
That's where it's going to return the upper 32 bits instead of the lower 32 bits of this, double 64-bit mess.
Right. And so it's useful if you're doing some math that involves very potentially very large numbers. You can actually make it work out correctly by using this operator to get the upper portion and do appropriate conditional checks or additional math to factor it in.
What's it?
It's not commonly used. to use this star. I mean, I don't think I've seen it more than once in code to get the upper 32 bits, but sometimes, when you need it, it's very handy to have.
Yeah, it's one of those sort of things where you're thankful it's there and you hope you don't run into having to use it. But if you do, it's, oh gosh, makes your job so much easier, because otherwise what would happen to those bits? They'd fly off into space completely useless.
You'd never be able to use them.
The best you'd have would be like access to a carry bit or something like that, right?
And of course, this is only in spin because we don't have multiply an actual 64-bit result. So it just is doing some work to figure this out.
Okay. I might just play around. I might just play around with it and see what happens to the numbers. So
yeah, well, it's just like if you have a really big number, like if you had the maximum positive signed value you could have, the 2 billion, 100 and whatever.
Yeah.
If you multiplied that by 2, it won't fit in a 32-bit number to be positive. What'll actually happen is it'll wrap around, right? And you'll get 0 or something. But what's really going on is that upper 64-bit, the upper 32 bits, has a 1 in it.
Yeah.
And it's because it's the upper section. You actually have to, say it's multiplied by 2 to the power 32 with that 1. So that's all that's what that means, right? The upper 32 bits is just the number will be how many times you've wrapped, essentially.
Okay. I will take that. I'll accept it. And then divide. This is so x divide equals y means x divided by y placed into x.
Right.
Okay.
And the same thing with just the modulus is the remainder of a divide. So if you had 5 divided by 6,
modulus is like the best thing ever.
5 divided by 2.
Well, 5 divided by 2, okay? So you get 2 and there's a 1 remainder.
Yeah.
Modulus will give you the 1 as the remainder.
Oh.
And how I always explain modulus is kind of like Pac-Man.
Yeah.
You know how you steer him out one side of the screen, he comes right back in the other?
Yeah.
That's your x-axis, right? So if you modulo x by, 12, and it's, some number larger than 12, he gets 12 across, and then it reps back to 0. It gets 12 across,
Yeah.
So that's what it does. It's an easy way to think about it. But this is how it actually works. It does the divide, and it returns the remainder instead of...
What do you do with the remainder?
The result.
Well,
say you're generating a random number with your question mark.
Yeah.
And then you do absolute value on it to make sure it's positive.
Yeah.
And then you modulo it by 12.
Yeah.
That's going to give you a number between 0 and 11, right?
Right.
Okay.
So you're taking a number from negative 4 billion to positive 4 billion. Is that the range we're talking about?
No, 2 billion.
2 billion.
Minus 2 billion.
So, again, I'm used to unsigned. So, negative 2 billion to positive 2 billion is what your question mark spits out. And you absolute value that. Now you know it's positive, whatever it happens to be. And then you do modulo by 12. You divide it by 12. And instead of it giving you the division result, it gives you the remainder, which is always going to be a number less than 12.
Yeah, that makes sense.
Yeah?
Right.
Yep.
It's so useful.
Yep.
It's very handy.
Yeah, it's very useful in things like encryption, too.
Yeah,
right.
I believe it. Okay. Yes, I get it. Limit minimum.
So the limit operators are saying whatever the value you give it, limit it to that value, to the value on the other side of the operator.
Oh, I didn't know the prep could do this. Cool.
So let's do an example.
So if you go click on the page there, 155, it has an example. X : y plus 21, limit maximum, let's do the minimum one first. I went to the maximum. So X : y minus 5, limit minimum 100. And what that's doing is saying subtract 5 from y, limit the results to the minimum value of 100. Right? So it means that the value that gets assigned into x is going to be 100 or greater, because the minimum is 100.
I see.
So in their example, like they say, okay, well, if y is 120, then 120 minus 5 equals 115. It's greater than 100, so x will get set.
Yep.
But if y is 102 in this example, the result of y minus 5 is less than 100.
So just set it to 100.
But 100 is what will get assigned.
I see.
I've always had to do this manually in other languages, so this is handy.
Yeah, it's really handy in Spin. They have this limit minimum, and then limit maximum is the other way around. It's if the value is greater than the maximum value, set it to the maximum value.
It's really useful for things like when you're trying to do bounds in nth dimensional space, like you've got, say, one line that you're bouncing something back and forth along, and the lower bound of it is 0 and the upper bound of it is 100.
Mm-hmm.
Normally you'd have to go, if the position on this line is less than 0, then the position equals 0.
Mm-hmm.
But with this, one line.
One line and you got it.
Right?
Yeah.
And it's one operator. You could literally just do x limit minimum equals 0.
Interesting.
Right? Fancy.
Because you can add the equals on and do it all in one operation.
Right. Interesting.
And the maximum being the same. It's really handy for like limiting a variable to a specific range, right?
Mm-hmm.
Or say you have like an LED that you're fading in and out between, off and on,
mm-hmm.
but you want it to fade in, but you don't want it to power the LED with anything less than 20% of the output.
Mm-hmm.
So you could limit minimum 20 on it. As the variable's counting up, it will always output 20.
Mm-hmm. At least 20. Yep.
And at least 20 until it gets over 20, then it'll start going up to 100. Right?
I get it. Yep.
Or whatever.
Very handy.
And it just keeps, like I've done that to keep an LED from going completely off, like a limit minimum it, even though I'm counting up and down. I think it looks better to not go, in some
all
cases.
The way off. Yeah. And then you can do like those fading in and then fading out, fading in, because it doesn't always have to go to 0 then. It can just go to like a dim state.
Mm-hmm. And that's using limit minimum and maximum
together.
Very handy. Okay.
So the next couple, it's actually easier to explain the standard shift before we do the arithmetic shift.
Okay.
So shift left and shift right.
Yeah.
I think Eddie's actually used these a little bit.
I think I've done it, but refresh my memory.
So what this is going to do is take whatever your variable is equal to and bitwise shift the bits, however many you tell it.
So let's do a 4-bit number. 1111.
Well, if it's all ones and you do a shift left, it's going to shift the ones up and fill in a 0 at the bottom.
So 1110.
Right.
And then if you bitwise shift right, it'll be 0111.
Right. Now that's for the regular shifts.
Right.
Now the arithmetic shift right, which there's only one of those because it only matters from when you're shifting from the right, because the sign bit is all the way at the top on the right side. And so what arithmetic shift right does is it fills in with whatever the sign is at the top. So if it's a negative number, it will stay negative. So in the case of your 4-bit number with the 4 ones, if you do a shift right, it's going to stay 1111 because it's keeping the sign bit.
Now, does the sign bit shift down like you said, or does it fill in a 0 after?
No.
It doesn't go 1011?
No, it stays. It takes the bits that are there and shifts them over and fills in with a 1.
Gotcha.
When the sign bit is a 1.
So when the
sign bit is a 0 and you shift in, it'll shift in a 0. So it's basically the value stays whatever sign it was to start with when you do these, or when you do the arithmetic shift right. So if it was negative, it stays negative. And if it was positive, it stays positive. And it all has to do with that top bit. Whatever value is in the top bit, that's what gets shifted in
So let's
to
say
the
you
empty
have
spot.
1010 and you do a bitwise shift arithmetic. Arithmetic.
Yeah, so if you have 1010, that'll become 1101.
1101. Because you're shifting to the right. Now,
Right.
let me write this down.
Well, so with a regular shift right, it would be 0101 if you shifted 1010.
With a normal shift, it always fills in a 0. With this, it fills in a 1 or a 0, depending on if it was a 1 or a 0 that was in that far left bit.
Right.
Instead of a 0.
Yep. So if there was a 1 in the far left bit, then it's going to fill in a 1 after it shifts.
So it'd be 1101, is that right?
Yeah.
Oh, I
if
see.
it was
I
a
get it.
0, it's going to be,
1
no,
0010.
Right.
Oh man. Okay. All right. I gotta write these down sometimes.
So that
Easy to
covers
keep
those
track of.
3, and now
Okay.
we're into your bitwise rotations.
And wait, I want to mention, because there's a lot of code, example code for, I believe, the XBs, in which there's a lot of bit shifting happening,
Mhm.
and like it translates to binary math essentially. And for those who have not experienced binary math, it's worth it to take a look at it, because when you bit shift to the left, so say 1111, right?
Mhm.
And you bit shift to the left, you actually multiply. Is it multiply the number by 2?
Mm-hmm.
Yep. You multiply.
Shift left is multiply by 2, and shift right is divide by 2.
Right.
But not
For each-
exactly, because you're spilling some stuff out of the top.
Right.
Right.
If you're dealing with a 4-bit number that is already full,
Yeah.
then it will not be multiplying, because you'll be shifting bits out of the top,
Right.
and it will mess up the value.
Yeah.
So if it's like,
And you got your sign bit up there too, so
Right.
keep that in
so I'm
mind.
trying to think, what's a good example of this?
It essentially means, like, if you have a large value and you shift it right or shift it left, it will actually end up wrapping and becoming negative, because you'll fill in the sign bit.
Oh.
But it makes sense, because it's the same thing as if you were actually doing a multiply, and the number would get much bigger, and it would go beyond the range of a 32-bit value and wrap around to the negative number.
Mm-hmm.
So it's the same thing. It's the same phenomenon happening there, is that you're wrapping the 32-bit number. You're just doing it with a shift instead of a multiply.
I think unsigned bits are much easier to deal with.
Yeah.
Yeah, well, I've been saying that for ages, but
Right.
Who listens to Whisker?
the signed things, they work out because of the way
Right.
that it's set up. It's just trying to wrap your head around it is
Right. It's a bit more complicated.
Yeah. I mean, that's part of the reason we had that big long discussion a couple weeks ago with the whole negative number thing. Part
Yeah.
of the reason that it's arranged that way is so that it will just work out when you do this regular math stuff on it.
So instead of it breaking when you get to the end, it wraps around the number space.
Right.
Great.
So
I
the
think I
next
get
two
it,
are
yeah.
really similar to the shift,
Okay.
except instead of when you shift in, instead of being a 0, it takes the bit from the other end and puts it on the other side.
Now this is like a group of Pac-Mans all chasing each other around the edge of the map.
So let's do
if you have-
1010.
Nom, nom,
Well,
nom, nom, nom.
If you do 1010 and you only go 1,
Yeah. It'd be
to
0101.
the left it will be 0101, because the one that was at the top there will wrap around to the bottom and
Okay.
fill in where you created the empty space by shifting.
Okay. And then if you do rotate
right,
right. So if
it's the
it's
same
originally
thing.
1010, it's still.
So it's whatever
Oh,
when
I
you're
see.
doing rotate right, whatever's in the bottom bit will
Oh,
get put into
it's
the
like
top.
a, yeah, it's literally like a wheel, what is it?
I
Wheel go
explained this
round?
already.
Is that wheel go
It's
round?
like a Pac-Man.
It's like a bunch of
merry-go-round.
Pac-Mans chasing each other through the edge of the screen.
It's a
But yeah, it's
merry-go-round.
like a wheel. I mean, you're just rotating them through. That's why they call it a rotate.
Oh.
Oh.
There you go.
It's like a diorama. You know, back in 3rd grade when you had to make like little dioramas? No such thing as PowerPoint back then.
So rotate's pretty handy too.
Yes.
Very
Now
nice.
the next one is
Reverse.
it has its uses. It's very handy, and it's one of the things that's fairly unique to Spin, having it as an operator built in
Okay.
to do bitwise reverse.
It looks like
And so
like a dolt face.
The smiley eyes, but it's basically whatever the bits
Operators
are
are not emoticons, Addy.
it reverses the order of the bits.
It's
So
serious
it's just that
stuff
simple.
here.
It
If you had,
reverses the order.
1100, it would become 0011.
Oh, you know what that sounds like? That stinking, I don't know.
Knot?
What is the knot? It's always
Well,
these
it's not-
knots.
But it's not the same as not, because it's not flipping the bits with each other. It's taking. I was just if you had 1110, that becomes 0111. It's reversing
Well, that
the
still
order.
sounds the same.
No.
Oh, no. Okay.
No.
I get it. I get it. No, I get it. All
It's
right.
taking the bit that was 1.
We'll get to
Yeah.
what happens when you knot every single, or did we already cover when you knot the bits individually?
Are you kidding me?
Yeah, that was the 2
That was
weeks
the
ago,
epic one.
forever.
Okay, yeah. I see.
Because that.
Are you
that is
kidding me, Whisker?
a unary operator. You don't do not as a binary operator.
Oh my
you
gosh.
do and or XOR. As
I was like,
binary.
no, I don't understand this at all. And then I did, and then I was happy.
Right.
Okay,
So
I get it. I get the reverse.
Okay. So the next 3 are and or and XOR, which are bitwise.
Now,
And
we've only
so
got 3 minutes here, just so
maybe
you're
we
aware.
should
Save this
Wrap-
for next.
save this to start into the next one.
Well, I can certainly keep talking about our trip. So today, we are leaving this afternoon. Well, the 10th. The afternoon, we are headed to Iowa to pick up Peter the Thinker. And then we're going to go to Grand Island, Nebraska. Putz around there, hopefully find some cheap diner burgers for Whisker.
Nom nom. Yeah.
Nom nom. And
Nom
then
noms.
I'm going to be like a Pac-Man going across the country from diner to diner.
It's
Tell
true.
you what.
it's true. And then we're going to make our way to Salt Lake City. And hopefully I'll get to drag race on some salt flats. That should be highly exciting. And then from Salt Lake City, we're going to make it to Rockland. And I believe...
We're going to go through Donner Pass. I'm going to try to eat Addie, but she's kind of...
I don't understand it. What does Donner Pass have to do
She's probably
with?
going to beat me up when I try to bite her.
What does that have to do? Well, Peter
Didn't you
might
read
be
in
distracted.
history about the Donner Pass stuff.
Nope.
Why it's called Donner? Oh, well,
Nope.
maybe you should.
Maybe
go,
a guy
take
named
some
Donner. Maybe a guy named Donner passed by.
He did. He was more full when he got down, but he had less family.
history. Yeah.
Oh, was this the cannibal dude who like ate to stay alive?
I'm not stopping at that diner.
It's people. It's people. Gosh, Soylent Green has never been so
Don't spoil it for everybody.
so alive. Everybody knows. Everybody.
So anyway,
knows.
at the same time that you guys are having your gallivanting trip across the states, there, I'll be hanging out with Chip at his walnut farm.
Fun. Are you gonna ride a tractor?
I might.
That's exciting.
I will definitely ride one of his off-road ATVs.
Oh,
now,
fun.
Chip's the guy that designed this chip that we're always talking about, you know. So if you have any frustrations about having to explain all this stuff, Roy, you could probably, he'll be within arm's reach.
Well, the thing is he's such a nice guy. He just like goes with everything. He'll help me explain it.
There you go. We should bring him on a first spin and be like, "Hey, I know you're busy, you know, running your company
he'll be
here,
kinda
but
busy. He's
how about
working on the
you
next chip.
step in and say hi?" He'd be like,
But
"Friggin' noobs."
He's actually a really nice guy. I don't think he
I-
would call you a freaking noob.
I believe it.
He would spend.
We should get him to do it just to say that he did for fun. Funsies.
Well, either way, it's not going to happen this week because we're out of time.
Out of time.
You can listen to this show
So
every
sad.
Tuesday at firstspin.tv. Until
Indeed.
next week, we'll see you guys later.
Bye.
See ya.